Yeah, thank you very much for the introduction. Ladies and gentlemen, I welcome you to my presentation, which is entitled Towards the Digital Twins for Panel Paintings, Final Element Analysis of a Prototype at Climatic Loading. First of all, I would like to thank the organizers, Michael especially, for inviting us and giving us the opportunity to present some of our works. Secondly, I would like to point out especially the contributions of Daniel Konopka, who is sitting here within the audience. In the recent past, we investigated quite a number of wooden cultural heritage objects. Some of them can be seen over here. So we have a pianoforte, which is about 300 years old, which you can find at the Händel House in Halle. We investigated a Cranach painting, 500 years old, or here the icon, one of the icons of the iconostasis at the Russian Memorial Church in Leipzig. The idea of the works is more or less always pointing in the same direction. Our idea is to develop numerical models which allow us to investigate these historic objects then within the computer and without touching the real objects at the end. These objects are hundreds of years old, and therefore, of course, we can find quite some damages within the constructions. We have very large deformations partially. We even can find some irreversible deformations, plasticity in the compressed wooden material. We have cracks that appear. And if the cracks appear in the paint layer of a painting, it's not critical from a structural point of view. Of course, the visual impression is disturbed here quite a bit as well. So therefore, the idea is to develop some numerical models which need to be formed out of all the different contributions. We need to collect quite some features, some information, which is the loading on the one hand side. The loading is usually the climate loading for these wooden constructions, so the relative humidity is here very essential. The temperature could be of influence. But of course, we could have some mechanical loading as well. The loading happened over centuries, of course, and it could change with respect to space and time. So it's quite uncertain what happened really to these objects. Then on the other hand, of course, we need to take into account all the different pieces which contribute to the construction. We need to get information about the different materials and the properties of these materials in order to be able to form a proper numerical model at the end. So the idea is to have a realistic modeling which could be used then in the computer to find out about the different loading conditions, which could be really very different in order to come up, for example, with climate corridors that could be applied to these constructions. But on the other hand, we don't want to touch really the real objects. So we would like to carry all these virtual experiments out within the computer and then come up with some useful conclusions for conservation and restoration at the end. So the goal is to develop, first of all, a virtual model which gives realistic results. So therefore, my presentation is split into the following parts. After this motivation, I would like to look and introduce into the material modeling. Then, of course, you can imagine we have quite a number of material parameters which have to be identified. And then I would like to introduce some structural applications to you. And at the end, I will finish up with some conclusions and our vision about the digital twin, which is the final goal of our developments. So let's start with an overview, first of all, about the different steps to be looked at. We have to start, of course, with a material model, with a material point, a characterization, with some continuum mechanical approaches. We need to check, of course, if the models are doing exactly what we would like them to do. Then we need the experiments in order to identify the material parameters. Then the big steps of validation start, which means we have some first simple structural experiments to be carried out. We have more complex ones. We will look into replicas. And then we will come up even with some really complex experiments using maybe some originals. The final goal of all the developments we are going to do is, of course, to introduce in the future a real digital twin of the objects, which is really quite complex at the end. I will comment on that at the end of my presentation. And it's more than just having a numerical model. We need a lot of information from the reality, which goes into the digital twin as well. And we need the so-called twinning, which means fitting the model to the reality. But let's start with the material point at the beginning with the modeling. As you know, wooden material is quite complex. Therefore, a lot of aspects could be looked at. We have, first of all, the elasticity. We have inelasticity, damages, plasticity that could be looked at and has to be taken into account. We have moisture. Everything is moisture dependent. Therefore, the moisture transport has to be described. We have hygroexpansion, we have creeping, time-dependent properties. The bond lines between the fitted different components of a structure have to be taken into account. We had already presentations on that. And then the uncertainty is a big issue on its own, which I will not look at here in my presentation, but the material properties are scattering. We don't know what happened over the centuries to the material. So the sharp deterministic model we are going to use here in this presentation is just a strong idealization, but in principle all the properties have to be described in an uncertain manner, and we have mathematical models available which are capable of characterizing the uncertainty. So the physics has to be modeled and the data to be used has to be modeled as well. Then we know, of course, that all the physical aspects are interacting with each other, and this way at the end we could have really a relatively complex description of our real object. When looking into the wooden material, we can approach it from different length scales point of view as well. We have the largest length scale, the macro scale, where we have the tree, where we have our objects at the end. We have as well then the mesoscale, where we can distinguish, for example, the early wood and the late wood, the annual rings. We need to look into the microscale as well, because we have here the cells and the cell walls, and the water is diffusing differently in the cell walls and in the cells. That has to be distinguished. Even though at the end, of course, we are interested into the macro scale, into our structural level, but we have the phenomena which are occurring on the micro scale to be considered as well and taken into account. So at the end, we implement our descriptions into the finite element context, which is a method to discretize our structures. And that ends up at the end into a system of equations, which you can see over here. We have the degrees of freedom for the mechanical part, the displacements. We have the two moisture degrees of freedom, and we have the temperature degree of freedom that can be looked at as well. These different degrees of freedom are coupled among each other, but in my presentation today, I will leave out the temperature degree of freedom because that would be too much time consuming that we don't have the time to talk about that. So this is the material model we are going to use. We are developing stepwise. We have the elastic contribution, and when we load our material beyond the elastic regime, we have plasticity, irreversible features, we have hygroexpansion, and everything can be summed up as short-term response. We have the long-term response, on the other hand, which is the creeping, the different levels of creeping, so the linear and the nonlinear one, and we have mechanosorption as well, which is then altogether the long-term response of our material. So let's look into the different components stepwise. We have small strengths, which is usually fine for our wooden constructions. We need to describe anisotropy, and due to the annual growing rings, we have a cylindrical anisotropy that has to be used. And we need to distinguish, of course, the different directions, radial, tangential, and longitudinal. When we load our material beyond the elastic regime, we approach the inelastic part, which means that we have irreversible contributions. We come into that plateau, as you can see here on the right-hand side in the stress-strain diagram. When we unload out of that plateau, we have irreversible parts of the deformation. And the plastic plateau yields at the end the fully compressed material when all the different cells are compressed and densified. So the anisotropic plasticity can be described, for example, with the Tsai-Wu criterion, which is a classical one, an analytical description of the yield surface. We developed later a multi-surface plasticity approach where we can take into account more realistically the different loading modes. We know that, of course, the material properties are strongly dependent on the moisture content. We have swelling and shrinkage. We need to consider the three different material directions for shrinkage and swelling. And the stiffness, the strength, the fracture energy, all are depending, so the mechanical properties are depending strongly on the moisture content as well. So here, for example, we see plastic multi-surface plasticity yield surface, and when the material's moisture content is increased, as we point out here in this slide, then the yield surface is shrinking depending on the moisture content and the material point. So that has to be implemented and connected to the moisture content. So then additionally we have the long-term response, the creeping. We have the primary creep with a decreasing deformation rate. We have the secondary creep where the deformation rate is kept constant, and we have the tertiary creep where the deformation rate, the strain rate, is increasing strongly. And all these properties are depending, of course, on the stress level applied. So we have an instantaneous, when we load the material, an instantaneous response which can be modeled by an elastic spring. Then we have the primary part of the creep, which is reversible, and when we load further, we are approaching the nonlinear, the irreversible part of the creeping, where we have plastic contributions, and we approach the tertiary part, where the deformation rate is really increasing strongly. It could lead at the end to failure, and the description is based on a strain energy density approach. And failure is approached when the red strain curves are suddenly going upwards and turning up. That's a situation of failure. So then we have here the hygroexpansion, the deformation-dependent hygroexpansion, which has to be characterized. We have a distinction between compression and tension. And the mechanosorptive creeping has to be accounted for, which is an increase of the strain even at constant stresses, but at a cyclic or changing moisture content. So in order to be able to describe the moisture-dependent properties in the material really in a proper sense, we need to know exactly what is the current moisture content in our material. So therefore, the diffusion and the exchange with the environment has to be modeled properly. We have the exchange with the environment via the surface that can be described via certain surface elements, and then we have the diffusion in the material, and we need to distinguish between the diffusion in the cells and in the cell walls. We have two independent processes which are coupled then at the end via sorption. And with the help of these two different moisture variables, we can get relatively realistic results at the end. So you can imagine having all these material models, we need quite a number of experiments which are capable of then to identify the features, first of all, and then secondly, the material parameters. So just to show you some, we see here stress-strain diagrams which have been obtained with investigating lime wood in radial, tangential, and longitudinal direction and at different relative humidities. From that, we could obtain, for example, the Young's moduli and the strengths. We investigated samples from different trees, and A, B, and C stands for the different trees. And you can see clearly that we have some kind of scattering even coming from the material, not only uncertainties which come from unknown loading cases in the past. But anyway, we neglect in this presentation the uncertainties, and we define here the Young's moduli and the strengths in the three different directions as a function of the density and the relative and the humidity in the material. So that can be used then in the simulation. Additionally, we need to identify the viscous properties. We used this experimental setup where we investigated the samples at different loading levels, stress levels. So we loaded, we have an instantaneous response, we observe what happens with respect to time, and then we unload again. And so at the end, we are able to identify the plastic, the viscous, as well as the elastic response of that material. And out of that, we then try to identify our material parameters. But not only the features of the wood itself have to be identified, we need to look as well into the paint layer. Here we measured the permeability, and we need to identify as well the structural properties of the paint layer. And as we heard before, there is a significant contribution from the paint layer with respect to the structural feedback. So then, after identifying the parameters, we can look into structural experiments. First of all, I mean, we take usually small experiments in order to have some basic states of deformation, some basic first comparisons with, for first validation with the reality. So depending on the different samples, if we have samples made out of different materials, painted and sealed on the one hand side and not sealed, we get the different deformation response with respect to time. And that can be compared nicely then to our, first of all, simple simulations. But it's more interesting, of course, to carry out complex experiments based on replicas. And one of our research projects was associated with this Cranach painting, 500 years old, which is relatively thin and has got a strong, very stiff support structure on the back. And due to the stiff support structure, a lot of cracks appeared over the centuries, which was disturbing, of course, the impression of the painting really strongly. So there was this restoration taking place. A modern support structure was suggested, and we developed replicas of the historic one as well as the modern one, so that we can investigate experimentally in the climate chamber on the one hand side, but on the other hand as well with numerical experiments on the other hand, the response of the structure and get a deeper understanding of it. So for the simulation model, we had to identify and describe really all the different features which contribute to the structural response. So that means on the one hand side, we even tried to model the annual rings in the panels. We took into account the paint layer and the panels itself and the support structure. We modeled, of course, the surface by surface elements. And then we carried out our numerical experiments. We took this climate, which was applied in the climate chamber as well. So we see here the stress distribution in the panel. And on the other hand, here the moisture distribution, which are relatively unhomogeneous distributed here in this panel. And we can see, of course, that features which are observed in the experiment, so these sliders were coming out at the edge of the panel, and this state of deformation was found, of course, in the numerical experiments as well. The nice thing is that we do not just get the total state of deformation or the total strains at a material point, but we can identify and split up the response of the structure at the material point, even to the different contributions. So we can take here our continuum mechanical description and have on the one hand side here the overall response. Here the black lines are the overall response, the summation curve of the strains at one location here at the back of the panel painting, and the other one is right beneath the paint layer itself. And these summation curves are formed out of the different contributions which are identified here, and the colors stand for the different rheological elements here as well. So they are summing up one step after the other, one contribution after the other. So here in this case, we did not have any plastic responses, so therefore that is left out. And we see the remaining colors, which are the colors over here. You are missing maybe the blue one, and the blue one is the difference between the pinkish one and the final one. So that has not been put on top on here. But with the help of these investigations, so we are able to address and understand really how our material is responding to which origin. So the nice thing is with our numerical investigations, of course, we can investigate different constructions, different situations, and play around in the computer without touching the real structure. And we investigated here, for example, the historic support, which you see here on the left-hand side. We will look into the damage of the paint layer. We look into the stresses that will come up in a minute that is encountered under the climate, which has been applied in the climate chamber as well. So we have the modern support. In order to compare it against it, we have simulated the situation having no support at all, and we compared it against the situation taking off the slider of the historic construction. So first of all, we simulate the first phase, which is the increase of the moisture content, and you see a quite typical response here of our construction. I mean, the gray colors here stand for the damage which appears in the paint layer. 0 means no damage, and 1 means totally damaged. And the stresses, I mean, the scale is given here on the right-hand side. And the result is quite typical. I mean, the historic support was really much too stiff. That's what we knew. And therefore, we don't have any state of deformation here, visible state of deformation. We have a strong dark color in the surface, so that means the paint layer is strongly damaged. Situation with the modern support is much different. We have, first of all, a very smooth distribution of the damage as well as of the stresses, but very much reduced compared to the historic support. On the other hand, of course, we have to get that due to some flexibility of the construction. Therefore, we have a kind of state of deformation. Having no support, the state of deformation is dramatic on the one hand side, and having no sliders, we have quite some state of deformation as well, but anyway, a quite inhomogeneous damage pattern and stress pattern as well. So next, we then reduce the humidity in our numerical experiment, and we get a similar result as we just saw before already. So that means we have here a relatively large deformation for the situation no support. With the support, we have a smaller deformation. Again, very rigid response with the historical one. And this way we can study really the structural mechanical behavior and the consequences for the damage potential in the structure. Here we investigate shortly the situation of the contribution of the paint layer to the response of the structural behavior. It was pointed out already before that the paint layer is, even from a structural mechanical point of view, significant. And we compare here the historic frame and the modern one. And we compare here the elongation and the deflection of the construction for both support systems. So what is given here is a state of deformation versus time. The bold black line is a full consideration of the paint layer as we try to be as realistic as possible. Then we reduced the thickness of the paint layer by 50%, and thirdly, we took off even the stiffness of the paint layer. That's all you can do, of course, in the finite element simulation. And then we get a really different picture, and it's significant with respect to the structural response. We then, of course, had some replicas as well investigated in the climate chamber, some experiments. Partially it's fitting, partially there are still some discrepancies. That might be due to the measurement of the state of deformation, because we took the replicas out of the climate chamber and had some photogrammetrical investigations. But that means that the current state, when we took the photos, is already changing, of course, the situation for the panel. So therefore, that might be some origin of the difference. Of course, there might be some needs for improving the identification maybe of the material parameters as well. So additionally, we put then some sensors, climate sensor in different depths of our replica. We have a sensor for the deflection and for the elongation. That's what we recorded for the climate, or for the moisture content in the construction. And out of that, we took then here, for example, the external climate, which was measured and which we took then here for the loading case in our simulation as well. We carried out the simulations. We have got here the deflection and the elongation. And what we varied here in this simulation, so the black line is exactly the experimental result, and in the simulation we varied some material parameters in order to find out about the sensitivity of the structural response. And what you can see, that small variations of already of the material parameters could change the response, the results, and give us some response which is fitting to the reality at the end. So therefore, there's quite a bit of sensitivity that has to be taken into account. So with our developments and our research, we think we are far from being at the end. The next step, and that's the vision, that's the outlook, we would like to develop the models as such further. That's one on the one hand side, but on the other hand, we would like to develop a so-called digital twin, which consists of different components. We have the reality, where we need to extract the information via sensors. That has to be used and combined with the information that we can get from our numerical simulations. We have an ongoing process extracting that information from the reality, and the numerical models have to be in an ongoing sense updated, and that's exactly what we call twinning. And this twinning has to go on while we are observing and monitoring our reality. And then we can draw our conclusions from the digital twin, which is then used in order to steer the reality. Now we can steer, for example, the climate in the museum. Or we can give some hints. If we are going on this way, there would be cracks over here and damages over there whatsoever. There could be a warning given. And then, of course, actions could be taken. So the cyber-physical system, at the end, that's our goal we would like to develop, but that includes, on the one hand side, really proper, good, realistic models, simulations on the one hand side, but we need to account for the reality as well by getting that information via measurements, via sensors, and we have to combine that information in order to come up with then the right conclusions at the end. So that's the goal towards we would like to work. So with that, I'm at the end of my presentation. And if you're interested, you can look up some of our results here via this QR code. I thank you for your attention.
Okay, questions up there?
There's a long-standing mystery with panel paintings, which various researchers have written papers with an explanation why they develop a strong curve over time. And the most common or reasonable explanation is the dynamic response to seasonal changes, which result in a plastic compression of the back of the wood so that it is slightly shrunk compared to the front of the wood. Have you looked at that in terms of your model? It would be very useful to know whether your model will predict long-term curvature, which is irreversible due to plastic behavior.
I mean, our models are capable of describing the long-term plastic behavior. Could be viscoelastic, but could be plastic as well. I mean, we are always interested, of course, in getting some real results in order to compare against with, but in principle, the features are implemented in the models. So we need to identify the parameters in a proper manner, and then, of course, we need the proper validation examples. But in principle, that's included. That's right.
Maybe I'll finish with this one. My understanding, which is very superficial of this area, is that digital twin is a term that's a bit like real or accelerated aging. It's a little bit fraught in this community. Is there a clear understanding of when you're allowed to say it's a digital twin and when you can't?
Sorry, I didn't get it.
What's it mean to be a digital twin? And is there a general understanding of what that means?
Yeah. I mean,
and when you shouldn't say it's a digital twin.
Yeah. There's somewhat definition available of a digital twin. It's more than just a numerical model. Huh? That's maybe it could be a shadow, a digital shadow or something like that. I mean, in mechanical engineering, digital twins are used for a long time. That's nothing new. I mean, that's a bit the tricky thing. But there are many areas where a digital twin could be implemented as well. In medicine, for example, you could have digital twins, which is critical maybe, but it could be very useful, very, very helpful, because you can get insights into processes and features which are not available. And digital twin means we have the reality on the one hand side, we need information from the reality, we need some predictions, could be finite element predictions, could be other models whatsoever, and these information have to be coupled. And usually, I mean, the structures we are investigating are changing, so therefore we need an update, of course, of the features of the structure. Therefore, this twinning is absolutely essential. And then, but that's so far just a digital shadow, what I described. The digital twin is active. The digital twin can give response, can warnings, can even steer maybe, the climate or whatsoever. And then, if there's an active way getting the information to the digital world and reacting from the digital world to the reality, so these both ways which should work automatically, that's a digital twin or a cyber-physical system, let's say.
Yeah, it's a high bar. Yeah. All right. Okay, thanks very much.